Welcome back to another exciting lecture. We're going to look at atomic notation and then some of the isotope effects that are sort of related to atomic notation. Right off the bat, what we're going to do, or what I'm going to say, is that we're going to adjust, and instead of calling this atomic notation, we should call it what it is more appropriately called, which is nuclear notation. And then we'll add the information to it that would actually make an atomic notation. So we're talking about the notation for individual elements. We're trying to come up with a symbology that gets us a lot of information very, very, very quickly. And where that's going to start is with our symbol. So our symbol is two letters, capital and then lowercase, or just capital in some cases. And we talked about those in one of our previous lectures. So hopefully you're now at a point where you've got some of those memorized or you're working through that. What we're going to add to that, not to memorize, but to realize, is this information about the atomic number, which is denoted as the letter Z, and our mass number, which is denoted as the letter A. Those two pieces of information will get included in nuclear notation. So if we look at the symbology noted down below, we've got our mass number written in the upper left-hand corner, and then we have our atomic number written in the lower left-hand corner. Those two pieces of information together give us some information about our both protons and neutrons. So we'll start with the mass number, which is the sum of the protons and neutrons. So what we would do for any individual element, we would add up the number of protons and neutrons, and we now have our mass number. If we go through and look at the atomic number, you might say, isn't that redundant information? And I would agree with you, because the symbol itself, once you know the symbol, you could look up where it was on the periodic table, and you know its atomic number, you know its number of protons. So why is there a need to include both of them? It may not be a need, but there is a bit of useful structure associated with it if we go through and consider what information we'd want to know about an element. So if we think back again to our previous lecture, we have our subatomic particles. In our subatomic particles, we have our protons, we have our neutrons, and we have our electrons. Electrons. If we know our number of protons, we would then know the element, hint, that's relevant for later. So if we know our symbol, we could use our periodic table to determine the atomic number and therefore know the number of protons. That would be our element Z, or what we've written as Z in the lower left-hand corner here. But we don't have the neutrons or the electrons explicitly stated within this. And again, we could go through and pick a corner and just assign them there, but we do something slightly different. So the mass number is what's chosen for that upper left-hand corner. Why would we place it there? Well, the mass number is the sum of the protons and neutrons, and if I have the protons plus my neutrons, we set up a little math equation, and then I subtract the number of neutrons in kind of an old school, longhand elementary school kind of format, we would get our protons. Well, if we note, that's kind of the exact notation format that we've got set up here. So they're set up in such a way that you could get the number of neutrons relatively quickly, mostly by inspection from the nuclear notation. Well, again, why not just put the number of neutrons in the upper left-hand corner? Then why have to do this calculation? And I think some of that has to do with the historical reasons on who would use this notation. Our nuclear notation is concerned about the nucleus. Well, who cares about the nucleus? Maybe somebody that cares about, I don't know, nuclear bombs. That's kind of a big deal. Those are those big explosions and things like that. So if we're concerned about radioactivity, we want to be able to look at our notation really quickly and efficiently and say, that's a really important piece of information because that's going to be explode. The number of protons and neutrons in and of themselves doesn't give us explosion. It's actually the balance between them. So knowing both our protons and neutrons is going to be useful. If we put the mass number, our protons plus our neutrons, right in the upper left-hand corner, that can get us information relatively quickly because of an artifact of how we read and write. When we talk about our English language or even German, what we'll note is that we read left to right, top to bottom. And so on our upper left-hand corner is where we're going to start our reading process. That mass number gives us a really big clue to the radioactivity of the element. The larger that number is, the more likely kaboom. So what we want to do is specify that information as front and center as possible so that we can actually visualize it, see it, and understand it and navigate through the system. Okay, so if that's what we're going to put in the mass number, then we have to go through and come up with ways to get to the neutrons, and that's the shorthand mathematical system we've set up. So that ticks off our neutrons are now covered, but now where do we specify our electrons? And this is the problem I've got, because if you go through and look at quote-unquote atomic notation, they very rarely continue on beyond what we're seeing on the slide right now. So where would that extra information be found? Well, if we consider the spaces that we've got, we've got a space in the upper left-hand, that's right-hand corner. I always have problems with that. And my lower right-hand corner. Well, could we specify more information in those spaces? Well, yeah. And even if you haven't taken a whole lot of chemistry or even know chemistry, you probably actually know inherently what's written in the lower right-hand corner. If you're like, you don't believe me, what's the formula for water? Water was H2O. What's written in the lower right-hand corner? 2. That lower right-hand corner is the amount of that element. Okay, the amount of the element in that compound. Since we're only looking at a single symbol here, there's nothing specified, and so it's an assumed 0, so nothing's written there. So that's actually where the amount of an element is specified, which would then suggest where should our electrons be specified? Well, they're going to get specified in our upper right-hand corner. And only sort of. What actually gets specified there is what's known as the charge of the element, which is the balance of our protons and our electrons. What do we mean by balance? Well, each of them contribute a different charge, positive and negative, to it. So it's how they affect each other. So there's a couple ways you could do it. You can look at a formula and say it's the protons minus the electrons, gets you your charge. Or you could go through and remember, so this goes back to the application that we talked about from our previous lecture, is that protons have a positive charge times the number of protons plus the negative charge of our electrons times the number of electrons will also get us our charge. And so that formula of protons minus electrons to get charge is really just a fancy way of taking the charge of the electron and instead of understanding where it is, inserting it into a formula so you don't have to think as much. Your choice. You can choose how you memorize charge or how you work with charge, but I would argue having the fundamentals to understand is going to be far more superior and allow you more flexibility in the grand scheme. Which then says, now that we have our protons, neutrons, and electrons defined, we now do officially have atomic notation. So again, I want to remind you that the charge and the amount that we've now added in here are things that aren't explicitly stated in most systems of atomic notation. Realize they are there, they are important, and we will use those locations throughout chemistry. They just aren't incorporated into the definition, unfortunately. So with that, we could do a little bit of practice. So on this slide, we've got the summary that we had before with our mass number, atomic number, and our symbol. We've got an example specified for you. You should be able to go through and tell me what the element is, the atomic number, what the mass number is, and the number of neutrons is or are, I guess technically for all of these. And so with that, I'll give you the freedom to hit pause, and then we can go through and just step through these. The element, hopefully you know now, is silicon, with our symbol of Si. The atomic number written in our lower left-hand corner is our number of protons, which means silicon has 14 protons. Our mass number is written in the upper left-hand corner. Got my left and right backwards again. In our upper left-hand corner, and that is again our 29. So we have 29 protons and neutrons. And so if we were to then consider our formulas for how you calculate protons, or just doing our mathematical symbols, okay, our mathematical longhand, we could go through and subtract A from Z in our notation, and we would get 15 neutrons. Okay, so hopefully that's okay as far as understanding. Realize that on a test question, you may be asked to flip it. So practice going backwards and forwards. And when I mean flip it, if you have an element with, let me cheat real quickly here, an element with 13 protons and let's say 17 neutrons, what would its atomic notation be? So you should be able to go through and process some of that. Okay. With that, we get to now kind of a big summary slide. This summarizes what we talked about in our last lecture, and it brings in a little bit of information about what we talked about in this beginning lecture. So you should be able to tell me the location, mass, charge, symbol for each of these, and you might now start being able to tell me some information about the meaning. At very least, you should be able to tell me the meaning of our protons. By the end of today's, and actually, I lied. You should also be able to tell me the meaning of the number of electrons. And by the end of the next however many minutes it takes me to get through, you should be able to tell me what it means to have the number of neutrons. When we talk through in the ordering here, the protons start the whole conversation off. So when I know the number of protons, something is defined. When I now know the number of electrons on top of that, something else is defined. When I know the number of neutrons on top of knowing the number of protons, something else is defined. Right? So all of this information is stashed on our, some of this information is stashed on our periodic table. We've got our symbol. You'll see the atomic number usually written above the element, and it can be anywhere above it, unfortunately, on the periodic table. That just depends on preference for notation. And then you've got the atomic mass written on the bottom underneath the element, anywhere on the underneath. That's interesting. Didn't we just talk about, I don't know, a mass number and an atomic number? But we said mass number, not atomic mass. Well, that must just be a typo. Unfortunately not. Believe it or not, I thought it was a typo. It's not a typo. Those are actually legitimately different things. The mass number is the number of protons plus the number of neutrons, period. The atomic mass is the average number of protons and neutrons for an individual element. But I can't change the number of protons because that changes the element. So when we're saying an atomic mass, it's really a difference in the number of neutrons. That's an interesting phenomenon. So if we change the number of neutrons, we change something about the nucleus, and therefore if we change it, we might want to come up with a name. And this is where we get isotopes. Hooray! By the way, that was an answer to a question earlier on in the lecture. So our protons define what element we look at. The neutrons define the isotope. We can kind of call this the type of the element. It's a little bit of a gray area there, but it's going to define how kind of heavy that element is. Atoms of the same element can have a different number of neutrons. Not always, but if they do, what we'll call these are isotopes. So if we were to go through and look at hydrogen, there are three isotopes, but let's say two isotopes of hydrogen. Right? One we call protium. We actually named the isotope differently. And then the other one we can call deuterium. Again, we named it. Most isotopes don't have a special name. The name for hydrogen is only coming up because we work with it a lot, or we work with it frequently enough that we want to be able to differentiate it. Because the only other way to differentiate it is to specify the mass number, which is our sum of protons and neutrons. Well, the mass number is conveniently written in the upper left-hand corner. I got it right this time. And so protium we could call hydrogen 1 and deuterium hydrogen 2. So the number written after the name of the element, so name dash number, that number corresponds to the mass number, which was our protons plus our neutrons. So when we're talking about hydrogen, there's two common isotopes. We get protium and we get deuterium. We would specify or see that information in our nuclear notation, and we could also see it in the name when written out. How many protons and neutrons does an atom of lead-206 have? This would be a good opportunity to pause again. And hopefully you've now had an opportunity. If we're looking at lead, lead is Pb, picked a tricky one, and 206 we could write in the upper left-hand corner because that's its mass number, as we just discussed. Lead is element number, as I pull out my periodic table, 82, which would be its atomic number, which I could write in the lower left-hand corner. And I could now go through and do the mathematics, subtracting 20 minus 8 is 16. I think I did that right. That feels a little weird to me. But let's just assume I did math. I did math horribly wrong there. 20 minus 8 for the record is not 16. Let's try that again. That would actually be, hopefully those of you were able to catch that, I think 112, which would get us 124 neutrons. So we've got 124 neutrons and we have 82 protons. That's what this notation as information gives us. Yes, you'll see questions on that. Okay, so if we then took this to the next level and said, we'll evaluate what's on the periodic table, what you would find for that atomic mass again underneath our symbol, is that you would find is that it's not 1 or 2. It's some weird fraction. It's 1.01. It was close enough to 1. But if you continue to go through and look, please do, at some masses for your individual elements, what you'll see is that those numbers can vary all over the place, and it's a little bit weird. And that's, again, because it's an average. So you're taking the average mass of all of the individual elements, which then sets us up with the next thing. If it's the average mass, let's go ahead and clear all of this. Delete all. Yes, delete. If we took the average mass of 1 plus 2, well, that would equal 3, but I've got two things I'm averaging, and I would get a mass of, let's break it down slower, 3 halves, or I would get 1.5. and yet our periodic table tells us 1.01. So something weird is going on. The periodic table is giving us an average, but it doesn't match how we would typically calculate averages. Well, why not? To understand that, we have to understand a couple complex pieces. Number one, we have to understand percents, and we need to understand averages. So let's take a hot minute to sidebar into those. Percents. So the first thing we want to be aware of is that percents provide unitless information. Okay, percents are the amount of one thing over the total. So one quantity over the total sample, and this would be what's known as a percent. Be a little bit grumpy here. Oh no, because I forgot to adjust something. So that's our percents. So some things that I want you to be aware of behind this is that if we were going to look at, say, 90%, what does that mean? What is the unit on that? Well, it doesn't have a unit. Why not? So we could call this a 90 points out of 100 points on an exam. And that would get us, if we did that math, 0.90. So 90 divided by 100. But that's not 90%. How do we get it? How do we get that percent back into the system? Well, you get that percent back into the system because what else do you have to include? Times the 100. Okay? And that sets you up with your 90%. Okay? Well, all of that information is actually stashed in this. Okay? So let's go through and break this number down. We've got a 90, and then it says percent. Well, what does per mean? If we look at writing this out, per means division. So if I have a 90%, I'm saying I have a 90 divided by, that's my per, and then cent. Well, what is cent? Century, centurion, centipede. Those are all in reference to the root 100. So a 90% is 90 out of 100. So we can use this information and kind of shift it and bring it into configurations that allow us to navigate certain problems. So within that, let's go ahead and delete all again. Do I clear ink? Yeah, that works. And we can look at an example question. We've got bronze. So let's pretend we've got a sample here. We've got bronze. So cha-chong, here's a chunk of bronze. And it's a mixture of copper and tin. Ooh. Okay, so it's got copper in here and it has tin. Okay, in this particular case, it doesn't matter about the symbols, but copper is Cu and tin is Sn. If the sample of bronze contains 79.2 grams of copper, so what we're now saying is we've got a bunch of copper in there. We've got copper being 79.2 grams. And then we have the tin, which is only making up 10.8, so it's making up a relatively smaller amount, 10.8 grams. What is the percent copper in bronze? Oof, okay, so we now have a question. What is the percent? And I'm going to change my notation a little bit. What is the percent of copper? Okay, well, if we're going to break this down, and technically in bronze, we're going to break this down. This is asking the one quantity. So the one quantity is how much copper is there per, and then how much total bronze is there. We probably should color code that a little differently. Copper and bronze. Well, if we're going to determine that percent, we would need to know the quantity or the amount. That means we have to know a unit. Okay, that unit can be expressed as mass or sometimes by volume, and that all depends on kind of individual perspectives of what you're measuring. If you're going to look at mass, you're typically looking at solids. How do we know we're looking at a solid? Well, one of the big hints is the unit that we see would be grams. If we're going to look at volume, percent by volume, we're typically looking at liquids or gases, and those, because they move everywhere, are a whole lot easier to measure by volume, which is why we would measure by milliliters, okay, or liters. So in this case, back to the question gave us grams, so we know we're doing it in mass, so we could even start to plug some stuff in. We could go through and say the grams of copper. And note, I'm not going to specify the number yet. I want to write down the units. So grams of copper. Do I know the grams of bronze in the total? It didn't actually tell me it, but it did tell me that these were the components in the total sample. So if I add those two together, oh goodness, doing longhand math, I should have prepared for this. I believe we get 90. And that would be our grams of bronze. So we do actually know that number. We could say this is 90. And up here, we'd say 79.2, because we've given all those numbers. We'll do the 0.0 for that. And we now know the grams, or the calculation for our percent copper. All we'd have to then do would be multiply by our 100%, and we now know the percent copper in our sample. How do we figure out how much tin? Well, that's going to change things. We could go through and say, well, in a 100-gram sample, I should probably have a calculator for a number here. If we had 79.2 grams of copper, and since I don't have a calculator, we'll just have to write it out, with 90 grams of bronze, if I had 100 grams of bronze, what would happen? Well, my units would now cancel, and I'd be left with, after this calculation, the grams of copper. But I want to know the grams of tin. Well, if I know the grams of copper, do I know the grams of bronze? Yeah, so I could say 100 grams of bronze minus, and I can't do that other math in my head, the grams of copper that I just calculated here, and I would now get my grams of tin. That would allow me to navigate both questions. Before I get the how much tin is in 100 grams, I would need a little bit of lead in, and that's where the percent of copper becomes relevant. So I would have to do that extra calculation. So this is how we can manipulate percents a little bit to do some simple kind of calculations. What we're now going to do is take that and apply that into our next system, making it even more complicated. So how do we make it more complicated? We're going to look at now our simple and weighted averages. So you've probably taken a simple average before, and in fact we already did in this lecture. If I wanted to know the average weight for the protium and the deuterium here, well, one of them weighs 1, protium weighs a 1, deuterium weighs a 2, there's 2 elements or 2 things I'm weighing, 3 halves, and I get 1.5. That would be a simple average. We just take the mass for each object, and then we divide by the total number of objects. That gets us our average. Weighted averages become more relevant if you're looking at a massive data set. So what if we weren't looking at just 1 protium and 1 deuterium? What if I had 15,000 of these and let's say 1,000 of those? Okay, well, that means when I go to add these numbers up, I don't want to do 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 for 15,000. And I don't want to do 2 plus 2 plus 2 plus 2 plus 2 for 1,000 times. So what I'd want to do is scale that up. And so in that scaling up, what would I do? Well, I could say 15,000 times 1. So this is kind of an amount by the, well, I guess we'll call it our average value that we're concerned about. And in the other case, we've got our amount times its value, and then we add that up, and then we would divide by, what are we going to divide by? Well, the total sample size. What was the total sample size? 15,000 plus 1,000 would be 16,000, and then this would get us our average. Well, someone went through and looked at that and said that that's still a lot of work. Is there some other way I could do this that takes into consideration percentages? Well, why percentages? It turns out percents are usually a little bit easier to determine than raw numerical values. So what they did is took this work and they tweaked it. Okay, well, what do I mean by tweaking it? So we're going to play around with some mathematics here. We're going to separate these two. So we're going to say 15,000 times 1 divided by 16,000 plus 1,000 times 2 divided by 16,000. Those are equal. What does that do for me? I don't get it. Why is that helpful? Well, what we'll further do, and I guess we'll color change as we manipulate further, is we can take 15,000 and we're going to put the 16,000 underneath it times 1. 1,000 divided by 16,000 times 2. And then we could go through and look at the individual 15 divided by 16, and that should look kind of familiar. That should start to ring a bell based off of what we did with our percents. What did we say percents was? Percents was our one substance divided by the total. Well, what is 15,000? Well, 15,000 was the one substance, our protium, divided by 16,000, which was the total. So interestingly, 15,000 divided by 16,000 is effectively our percent of our protium times the mass of protium, plus our 1,000 divided by 16,000 is our percent of our deuterium times the mass of our deuterium. This simplifies our overall numbers, because now I'm not dealing with 15,000 or 16,000, and when we talk about chemistry, those numbers are actually pretty darn small. We're usually talking about even larger numbers than that. We can convert those numbers into something more reasonable as a value between 1 and 100 for our percents. And that's pretty powerful. And so that's what this weighted average is. Instead of going through and adding every single number, what we're going to do is take into consideration how much that number appears in our total, and then we'll convert that into a percent. That's now the weighting factor behind it. What does this mean for us? Well, I'm going to clear all of this again. So let's clear our ink, and it's going to take us to a formula. Because what we're concerned about here is our atomic masses, so the mass of our elements. What we're observing is the mass of our particles. So the percent or percent abundance of whatever our sample is, A, times the mass of A, plus the percent of the next thing, B, in this case protium and deuterium, times the mass of B. Well, could I also have a third thing controlling this? Yeah, you can. That does make things a little bit more complicated, and at least for Chem 130, we typically don't see that, but you could go on and add as many things as you wanted into this average. And then when we put this all together, this gets us our average mass, okay? Or in our case, the average mass number. And that, my friends, is the atomic mass, and the atomic mass is what's found on the periodic table. And why? Because when we look at an individual sample of hydrogen or iron or helium or any element, what we're going to get is a big collection of different isotopes. Those isotopes are things that are determined by nature, not by us. So we can't control those very well. So if we're looking at a random sampling, what we're going to want to know is the average mass of that sampling, not the exact mass for each individual element, because we don't have elemental control. So this formula is now going to become super, super critical. And what I'll do is underline the important parts. Is going to be super critical for you to know and be able to use to be able to calculate things. So how can we actually see this with our protium? Okay, I don't have this 100% nailed down. Oh, and it deletes permanently, so I don't have an undo. But if we go through and look, protium is about 99% of all of our hydrogen. Deuterium, on the other hand, makes up about 1%. So what does this mean for us? If I take 99%, so per 100, and I multiply now by its mass, that 1, and then I say, well, I have 1%, so 1 per 100 times the deuterium mass, which was 2, I would then get the atomic mass. And if I go through and run this calculation, we're going to get 0.99. And I tried to do better about color coding the older I get. It'll fail eventually. 0.99 plus, I wish I knew the math on that one, but actually I do know the math on that one. It's going to be 0.02. I think I did that right. And then we do the math to add this up. What do we magically get as a final answer? We get 1.01, also known as, ta-da, the atomic mass for hydrogen. So an individual sample for hydrogen is mostly protium. Okay? Again, name not super important, realizing that it's hydrogen, and hydrogen 1 is the primary isotope that we're seeing. But that's how we would manipulate our averages. So with that, we'll set you up with, yeah, of course it's going to leave all that. So we're going to delete everything again. So we'll clear ink, and we'll leave you with a potential example here. In a second, hopefully you'll see just the answer magically appear with no explanation, which means you should spend some time to actually solve this on your own, and then go through and match that to the work that I've got written out. Okay? And ta-da! You get a whole bunch of work now on screen, showing technically two different methods, so we'll talk through each of them. So on the left side is where I would start. So where I would do is first thing I did when I got a test is I would write down this formula because I'm going to forget it eventually. And now I would start to plug and chug. So percent of A would be the first thing I see. So gallium 69, 68.926. Note, I underlined it in red and then wrote the number in red. Why? Because I want to color code and keep that information as tied to each other as much as possible. Colored pencils, pens are a good option for trying to solve these questions. The next part that number I encounter is our 60.11, which is the percent abundance for gallium 69, so I can put that into my formula. And then we have gallium 71, which would be the other piece. So plus, we had to get the percent of that times the mass of that, and then equaling to the average. Okay, but if we read through the rest of the question, it doesn't, well, if we read through it, it did not give me the percent of gallium 71, and it doesn't give me the mass of gallium 71. The question then says, what is the mass of gallium 71? Ooh, dang, I need to solve for the mass of B. That's why I wrote an X. Any kind of variable works. You want to draw a pineapple? Draw a pineapple. That's fine. Okay. How do I figure out then that percent of B? Well, there's two isotopes. Total needs to be 100%. So I can take my 100% total minus my 60.11. That'll get me my 39.89. That drops that percentage in there. Where do I get the average from? Remember, the average is found on the periodic table, which I'm going to complain about over here in a second. So all you got to do is find your periodic table, write down the number for the atomic mass for our periodic table, and we write that down. It's now just a question of going through and doing the algebra, and we get an X of 70.92. Well, does that average value, or does that value make sense for gallium 71? Well, gallium 71 has a larger mass number than gallium 69. So should its mass be larger? Yeah. How much larger should it be? Well, gallium 71 has a 1 unit mass difference. So we're going up about 1. This is showing about 2. Like, that's not too far off. So we're probably actually good here. Right? And so what we're trying to navigate is how we would align that and then kind of by inspection, make sure our number's right. There are other formats that you could run. So this is the preferred format that I like to use. Percent A, mass A, plus percent B, mass B in one long line. I have heard tell, and several colleagues actually comment that they like this formula where you do percent A, mass A, plus percent B, mass B underneath. And then you would do at the very bottom, your average would be at the very bottom of this. The problem that I have with this comes from this very, very question. Okay, this is our atomic mass from our periodic table, and that when I go through to plug and chug, this format is really only valuable if what I'm solving for is the atomic mass that's found on the periodic table. Why would I have such a problem with that format? The atomic mass is on the periodic table. It's there already. Okay? And while an instructor could write a question that what they're asking you to do is solve for the atomic mass for an unknown element, generally speaking, we aren't that creative. And what we're asking you to solve for is based off the numbers that we've already found in reality with these actual elements, which means you can cheat your way through the question by just looking at the periodic table to get the number, not actually run on any of the calculations. But I didn't tell you that. Okay? That said, I'm aware of that cheat, and so I will look up different numbers. So again, this is the formula that I would highly encourage you to go through and memorize when dealing with our weighted averages. With that, I believe we've talked for way long enough, and we should be done with the lecture. So I hope you have a great day, and we'll see you for the next one. Bye-bye.